Hi, it's time for another math easy solution. Today I'm going to go over another epic long video, and this is going to be on cylinders and quadric surfaces. And yeah, before we get to it, like always, if you don't have time to watch the whole video, you could play this video at a faster speed. Top secret life hack: your brain gets used to faster speed. There's a link to my tutorial, and yeah, you can also download and read the notes in PDF format or in article format on the Hive blockchain, and you can also watch the video in parts. And timestamps of all the parts are in the description, as well as a video sections playlist, which I will make after I upload this, and I'll upload parts of this video by video. And again, all the links will be in the description below. And yeah, including the timestamps where you could skip even this intro and so on, where you can go whichever part you want. And yeah, let's just dive right in. So calculus book reference. Note that I mainly follow along the following calculus book, and this is Calculus Early Transcendental, 7th edition by James Stewart. And note, in the earlier videos, I used the 6th edition. All right, going further. So sections in calculus book chapter. So I've made a list of the sections in this particular chapter with links to the Hive post of the videos I've already finished, including the playlist links as well. So note that I've started splitting each long video into sections and made a playlist for each. So here's the vectors in the geometry of space playlist. And this includes so far 6 videos, including this one right here. Actually 6 sections, but then each one has some of them have subsections. And so the current one I'm doing right now is cylinders and quadric surfaces, and there's a link to the playlist as well for as I'll upload all those videos after I upload this one, and so on, and I upload those slowly. Anyways, let's just jump right in. Alright, so topics to cover. So note that the timestamps will be included in the video description for each topic listed below. And so first section is going to be cylinders and quadric surfaces. And then we're going to look at cylinders specifically. We'll go over example 1 on parabolic cylinder, example 2 on circular cylinders. And that involves 2 parts, vertical cylinder and horizontal cylinder. And then also note 3D surfaces versus 2D traces. Just important note there. And then we'll go cover quadric surfaces and look at these examples. Example 3, ellipsoid. Example 4, elliptic paraboloid. And example 5, hyperbolic paraboloid. It's hard to pronounce these. Example 6, hyperboloid of one sheet. And then go over some computer drawn graphs of quadric surfaces. And that is in table 1, graphs of quadric surfaces. Then go over example 7, hyperboloid of 2 sheets. Then example 8, elliptic paraboloid, and then go over applications of quadric surfaces. And then the last part, exercises, we'll go over exercise 1, modeling Earth as an ellipsoid, and look at Earth's ellipsoid equation, and then parallels or circular lines of equal latitude. And then the last part is the meridians or elliptical lines of equal longitude. And then look at the last exercise 2, hyperboloid, hyperbolic, I think this should be. Yeah, it should be a hyperbolic paraboloid generated from lines. So that's pretty epic stuff there. So now let's finally jump right into the first topic, and that's the cylinders and quadric surfaces. So we have already looked at 2 special types of surfaces, planes and spheres. And basically, here's just recap my earlier videos, it links to the playlist. And this vector equation of a plane, so you have like this, basically you have a vector that's on the plane, and then a normal vector, and then you have a vector from the 0 point axis, and from there you can get this equation right here of the plane. So then the dot product of this vector with this vector, normal vector, is going to be equal to 0 based on the dot product properties. And then scalar equation of a plane, you can write these out without vectors, and it's going to be like this. So a times, pretty much a times x plus by plus cz, and this is assuming that this distance is going to be on the 0 point. Yeah, on the origin. All right, and that equals to 0. So then the equation of a sphere, to recap, this is if you have a center at the origin, the equation is just going to be x squared plus y squared plus z squared equals r squared. But if it's not at the center, if you have a point like, let's say, at C right here, which is h, k, l, you're going to have subtracted here, n equals r squared. Similar to this one right here, this is at a distant point. But if it's at 0, you could just remove all these x naught, y naught, z naught. All right, going further. So here we investigate 2 other types of surfaces, cylinders and quadric surfaces. In order to sketch the graph of a surface, it is useful to determine the curves of intersection of the surface with planes parallel to the coordinate planes. These curves are called traces or cross-sections of the surface. Alright, so now let's take a look at the first section that's going to be on cylinders. So a cylinder is a surface that consists of all lines called rulings that are parallel to a given line and pass through a given plane. And to illustrate that, we'll look at the example right here. Example 1, parabolic cylinder. And this states, sketch the graph of the surface z equals x squared. Alright, so let's take a look at the solution. So notice that the equation of the graph z equals x squared doesn't involve y. This means that any vertical plane with equation y equals k, which is again parallel to the xz plane, I'll illustrate this with a drawing, intersects the graph in a curve with equation z equals x squared. So these vertical traces are parabolas, are all parabolas, or just are parabolas. The figure below shows how the graph is formed by taking the parabola z equals x squared in the xz plane and moving it in the direction of the y-axis. Alright, so let's draw this in 3D. So it's going to look something like this. So we're going to actually have a horizontal, like parabolic cylinder, that's what it's called. It's going to go like this, and I'll draw the axis, etc. soon. And just illustrate this. So this goes like this, and this goes like that, and this goes here, and just go dash line through it. And then, so the z-axis is going to be, let's say this is the center, z-axis, and it goes all the way down here. And it goes all the way here because we have z equals x squared. Yeah, so when you plug in 0 for x, you're going to have z as 0 as well. So it's going to go all the way down to this bottom there. So that means the y-axis is going to be directly on this. And this is going to be x right here. It doesn't matter what the y is, etc. So this one, when z is equal to 0, and I mean when x is equal to 0, z is also equal to 0, and y is every single value. So basically on the y-axis, like that. And yeah, that's how it looks like. And then these are all parabolas. So when you have y equals 0, it's going to be directly on here. I'm going to draw this for the origin like that. And this is going to look something like this. It's all going to be basically parallel parabolas. And go like that. Actually, yeah, this is a through like that, and then dash line across there. And yeah, that's how it looks like. All right, so now the next setup is we're going to draw the ruling. So remember the definition right here. These curves are called traces or cross sections, and then actually this part right here. A cylinder is a surface that consists of all lines called rulings that are parallel to a given line and pass through a given plane. So this is the plane. All parabolas right here, all basically make infinite parabolas along the y-axis, and then you're going to have rulings all parallel, basically a bunch of lines. It's going to be parallel in this case to the y-axis. It's parallel to this y-axis, like that. So you can draw this out through basically infinite amount of these lines like that. I'll just let's put it on this side right here, etc. So on the outside, just draw those lines. Basically, have infinite amount of that, and I'll just put it in red right here. These are the rulings, and they are parallel to this y-axis line like that. Alright, so going further, so here's the graph in GeoGebra's 3D graphing calculator. So there's a link here, and I'll include basically all the 3D graphs that throughout this whole video, etc. inside. So you're going to have over here, this is how it looks like, and if you go to this link right here, and you're going to have a whole bunch here. These ones are for the other examples and exercises. So here's how it looks like. So if you just go, you can just type in the GeoGebra z equals x squared, and it's going to create just a cylinder like that, and it's parabolic cylinder. That's epic stuff like that. Yeah, sweet. Yeah, it's pretty sweet. Then you can zoom in and shift it around and rotate it and so on. You can do some other stuff like that, move it around. And yeah, you can play around with it, and yeah, pretty cool stuff. All right, let's continue further. So the graph is a surface called a parabolic cylinder made up of infinitely shifted copies of the same parabola. Here, the rulings of the cylinder are parallel to the y-axis. So, going further, so we notice that the variable y is missing from the equation of the cylinder in example 1. This is typical of a surface whose rulings are parallel to one of the coordinate axes. Yeah, so if one of the variables x, y, or z is missing from the equation of a surface, then the surface is a cylinder. So that's a good note right there. Yeah, because basically whatever shape you have, then it's going to be extended out infinitely. So the y is missing here, and so this means that we're going to extend this out for whatever value of y there is. So that brings us to example 2. This one says, identify and sketch the surfaces. So here, yeah, we have two parts, part A and part B, and this one is right here. So we'll look at part A right here. And yeah, actually, first off, I just updated the description. So these are examples we're going to be dealing with circular cylinders. And then the solution to part A, this one is going to be a vertical cylinder, and I'll show that soon. So we have x squared plus y squared equals 1. So notice the z is missing. So since z is missing, and the equations x squared plus y squared equals 1 is just a circle, yeah, where in this case z equals k. So we have whatever value of z you're also just kind of a circle that's shifted based on the value of z. So this represents a circle with radius 1. Because remember, the equation is going to be r squared. Yeah, so that's going to be the r. So I'll put this like that: r squared with radius 1 in the plane z equals k. And the surface x squared plus y squared equals 1 is a circular cylinder whose axis is the z-axis. Yeah, so that means that we're going to have rulings that are vertical lines. So let's just draw this out. So we're going to have a cylinder. What I'm going to do is, so it's going to be a vertical cylinder like this. And then we're going to have the z-axis goes through on the top like that. It's going to look something like this. Because remember, we're going to have a circle. I'll illustrate this as I go. And this goes all the way down into here. And then this is going to be dash like that. This is going to be the y-axis. Dash like that. This is going to be the z-axis. Like this. So that's z and that's y. I mean, yeah, that's z, y, x. Like that. And the rulings, yeah, they're going to be vertical lines. But again, I want to point out right here. So this is just the equation of a circle right here. So if you have z, let's say z is any random value. So let's say z is right here. And so you're basically going to have a plane like that. That's going to be across it. Dash like that. And this is going to be at the z equals k plane. And in there you're going to have a circle. Like this. And this circle is going to be, they're all the exact same equation, but depends on but then the z equals k value is just different. That's going to be, we just put a slice like that. And all of these circles are going to be just x squared plus y squared equals the radius r squared equals 1. So in other words, 1 squared is just equal to 1. So the radius is all 1. So then this point right here is going to be, so this point right here is going to be, yeah, radius 1. So it's going to be 0, 1, 0 like that. This point is going to be at the 1, 0, 0 like that. And so on. So that's how it looks like. And then the rulings is just going to be straight across like this through it. It's going to be all in there. Put a dash through this plane to make it. And these are all the rulings across it. Dash, dash, go straight through. Oops. Yeah, like that. Yeah. I just fix that up. So you're just going to have vertical rulings. And there's the ruling. So vertical rulings. Alright, so that is what we have. So the next thing is, like always, we're going to graph in GeoGebra. So it's going to look like this. So z equals x, or actually this is right here. So x squared plus y squared equals 1. You're going to have a vertical tube like that, just a cylinder there. And if we go to this, you just press this and then go to this one. So there's our cylinder. Set our number the points at 1, so it's radius of 1. Straight across. So there's x squared plus y squared equals 1. All right, that's pretty epic stuff there. And yeah, so now let's look at solution to B. this is going to be a horizontal cylinder. If you look at B right here, so now we have y squared equals z squared equals 1. So now the x variable is gone. So that means x could be any value. So in other words, we're going to have a horizontal surface, or in this case, cylinder. So in this case, x is missing, and the surface is a circular cylinder whose axis is the x-axis. It is obtained by taking the circle y plus y squared plus z squared equals 1, and x equals 0 in the y z plane, and moving it parallel to the axis. And we could see this over here. So we're gonna draw this out. I'm just gonna draw this line, this cylinder horizontal like that in 3D, and it's gonna look like this. Then the z-axis is gonna go. There's the z. This goes all the way down, and then it's the x is going to be x is going to be the just a variable that's not in the equation. So basically, these are all independent of, all these shapes are independent of it. So we're going to go all the way along it. So it's going to look like this. This is going to be our x, and it's going to be a tube like that. Yeah, it's going to be a tube like that. This goes all the way down here, like this. And at this point right here, where you have x equals 0, you're going to have this point is going to be 0, and then the y is going to be, well, 1. The radius is 1. This is going to be here. This is going to be 0, 0, and then 1. And this is just a circle like that, and we just shift it across all throughout. There's our circle like this. Y squared plus z squared equals 1, and x is equal to 0 at that point. And then you just shift it all the way across this entire thing like that. And then the ruling is just going to be a horizontal line across the whole thing, basically parallel to the x-axis and so on, like that. Just going to put them all across like that, and that's how you make this tube or this horizontal cylinder. All right, so that's what we have, and then as always, you can graph this in GeoGebra 3D graphing calculator. It's going to look something like this, just a horizontal tube. So let's just go over here, we click this, and then go to this one. Again, this link has all of the exercises and so on, or pretty much all the 3D ones. And there's the tube like that. And you can see the values of 1, radius 1, and so on. Epic stuff there. And this one, there's no x. There's no x variable in this one, so that means all the x variables are going to have the same shape, which is the circle. So it's just basically infinite circles. All right, so that's pretty epic. And going further, I just want to make a note. 3D surfaces versus 2D traces. So when we are dealing with surfaces, it is important to recognize that an equation x squared plus y squared equals 1 represents a cylinder and not a circle. And the trace of a cylinder, x squared plus y squared equals 1, in the xy plane is the circle with equations x squared plus y squared equals 1 and z equals to 0. So that's the thing. It's very important to distinguish when you're dealing with 3D versus 2D. So so this is when you're dealing 3D, this is a 3D surface, and that's made up of infinite circles that have basically the same equation plus the variables define it for the z, the missing one. So z is equal to 0. You can have a million of them like that. This one right here at this point, and you have a million, or in this case the z. Whatever the z value is, you're going to have a million of these. So this is a circle, but the full shape is going to be a cylinder. So that's the important thing to keep in mind at all times. All right, and now let's take a look at quadric surfaces. So a quadric surface is the graph of a second-degree equation in 3 variables, x, y, and z, or z. The most general such equations, basically this just means a power of 2. So the most general one, it's going to be something like this, ax squared. So the a is just a constant. You have that power 2 right there, indicating it's a second-degree equation. The next one's going to be another variable, b, another constant b, then squared, plus c z squared, and then to account for other stuff, you're going to have the letter D for x, y. It's going to get super general, plus E, Y, Z, plus f x z. So basically accounting for all the planes here, x, y, then there's x, z, then these two together, y, z, like that. And then plus gx plus hy plus z, I, z plus j equals to 0. All right, yeah, going further. So where A, B, C, D, E, F, G, H, I, and then J equals to 0. So yeah, so this one's multiple. You have the constant and then each variable, and this is just general and without any variable as well, like that. But by translation and rotation, you could if you just rotate the surface and move it around, it could be brought into one of the two standard forms. That's going to be the first one, ax squared plus by squared plus cz squared, and then plus j. So basically, you can shift it all around and do a bunch of manipulation, and then just to get it, basically get rid of all these there, and it just equals to j. This equals to 0. So it's just standard stuff. And then, or you could also write it if one of them doesn't have a squared. You could shift it around, rotate it, such that you're going to have an ax squared plus by squared plus iz, like that, equals to 0. So that's this right here, iz, like that. So you could have it one of these two forms. All right, so that's pretty interesting stuff there. All right, so yeah, that's the quadric surfaces, and also I wanted to add another note here. So we can get from here to here by translation and rotation, and also completing the square. So you usually have to just complete the square first. So and I'll show that in some of the examples. And then once we complete the square, then you could shift it or translate it, and so on. And this is basically getting rid of just more difficult constants, etc., just so we have something simple like this. That's what the rotation and translation does. Alright, so going further, so quadric surfaces are the counterparts in 3 dimensions of the conic sections in the plane. And this is linked to my playlist on conic sections and so on. So here's the counterpart in 3D. But so in 2D, these are conic sections. So you have a cone like that, and depending how you slice it through with a plane, you'll get a different shape. So a parabola is vertical down this cone, and you get, this is a hyperbola. Hyperbola, you'll get two parabolas like that. Or basically, a hyperbola is this shape going vertically down. Parabola is going at an angle, so you only cut one. And then an ellipse is you only cut one, but from both sides. This one, you cut it all the way to the open side. This one, you cut it such that it cuts through one, but fully on both sides. So you're going to have an ellipse like that. That's pretty epic stuff. And a circle is just an ellipse that's perfectly horizontal cut. All right, going further. So in a parabola, in the equation form, it's going to look like this. Y squared equals 4ax. It's a standard form. Yeah, that's actually interesting. I haven't seen that format before. But basically, you're going to have one variable and then the other variable not squared. One is not squared, one is squared. That's pretty much it. And then a constant somewhere. All right, and then an ellipse is going to be like this: x squared plus x squared divided by a squared plus y squared divided by b squared equals 1. And yeah, I'm just recapping on this because we're going to be dealing with a bunch of these conics like that. And this equals 1, and this is the ellipse. And these a squared and b squared are different, but if you have them the same, then that means you can move the a to the other side, and you will have a radius. So radius is going to be a squared. That's an ellipse. So a is the horizontal, and then b is the vertical. So notice basically the vertical radius, horizontal radius, and they're different. And then circles, they're both the same. They're both a. And so in a hyperbola, instead of a plus like this, you're going to have a minus. So that's the minus. And the a's are going to be here in the horizontal. Like that, this equals to 1. So that's pretty epic stuff. Yeah, so you have this x squared divided by a squared minus y squared divided by b squared. But then if it's the other way around, if it's y squared minus that, you're going to have a vertical hyperbola. So that's an equation of conic sections. There's a link to the image I got. Anyways, let's go further. Yeah, and now look at the example 3. This is on the ellipsoid. So use traces to sketch the quadric surface with equation right here. So x squared plus y squared over 9 plus z squared over 4 equals 1. All right, so let's take a look at the solution. So solution by substituting z equals 0 we find the trace in the xy plane. So yeah, basically plug in a 0 there and then see what happens to that. And let's look at this. So if we plug in z equals 0, so we're going to get a x squared. X squared is nothing like that. Then y squared over 9 equals to 1. And this is just an ellipse, actually. This is just going to be an ellipse. We'll put that on top here. Ellipse. So you can see how it's written. So x squared over, I just shifted the stuff around to put the ellipse at the bottom. So you're going to have an x squared, for completeness, x squared over 1 squared, which is just 1, and it just equals to x. Doesn't change anything. And then the next one's y squared equals to, well, instead of 9, we could write 3 squared, and this equals to 1. So there's our a is 1, and then our y is 3. So you could see that, our b is 3. So there's an ellipse. X squared divided by a squared plus y squared divided by b squared equals 1. So we have an ellipse like that, and this is for z equals to 0. So yeah, this equation, when we plug it in, we get this trace, which we recognize as an equation of an ellipse. So in general, the horizontal trace in the plane z equals k. So when you have the vertical one, it's going to be a horizontal plane, and you're going to have the equations inside there, like that. It's going to be a horizontal trace. In the plane z equals k is going to be, so instead of z equals 0, we're going to have z equals to k. So at z equals to k, we're going to have the horizontal traces. That's going to be this equation, x squared plus y squared over 9 equals to 1. And then we also had this right here. This is the z squared divided by 4. So instead of 0, we're going to put in k and then shift it over to the other side. We're going to have minus k squared over 4. K squared over 4, like that. And yeah, so this equation, this is an ellipse, provided that k squared is less than 4. That is, the absolute value of k is going to be, well, less than 2. So in other words, k is between -2 and 2. This is so that the right side isn't negative or 0, since the left side is always positive. So in this case, we always want this to be, because the left side is always positive. So this part right here, because you have an x squared, so whatever you have in there, you're going to have a positive number, and y squared is going to be a positive number. So it's going to be greater than or equal to 0. And this part right here, we need it also to be greater than or equal to 0. And this is so that, basically if you look at it right here, so k squared, if k squared is, it has to be less than 4, so that this value is going to be less than 1. And then 1 minus that is going to be, positive. So it's 1 minus a number smaller than 1, you're going to be positive, so it's all equal to 0. And this 0 part, we don't want it to equal to 0 because we want the ellipses, but if this is somehow equal to 0, you're going to get a line, because this will be x squared plus y squared over 9 equals 0. Move this around, you'll just have a y equals x type of line, but with a 9 somewhere there. It's actually just going to be a trivial result, and we'll just look at the ellipse side. And this becomes an ellipse because, well, you can write this in this format. So this ellipse right here, this is how the format x squared divided by a squared plus y squared divided by b squared equals 1. So you can get this format by dividing out the right side by itself, and then do it to both sides just so that we get 1. For example, I'll just do an example right here. We have, let's say we have k is equal to, k is equal to 1. So if we have k equals to 1, we're gonna get x squared plus y squared over 9 equals to 1 minus, and then we'll have k squared as 1. 1 squared is just 1 divided by 4 times by top and bottom. This equals to 4 minus 1 is 3 over 4. So to get it in the standard form, well, we just divide this out by 3 over 4 on both sides. And we're going to get x squared over 3 over 4, like that, and then plus y squared over, this is going to be 9 divided by 3 over 4. Well, 3 over 4, it's going to just go inside it. So we're going to go, we're going to go 3 over 4, but then you could just multiply the 3 by the 9, you get 27 over 4 equals to 1. And these ones, you can obviously write these as square roots, and so on. Yeah, square roots and then squared to get the radius, and this is going to be our standard form, like that. And this is just an ellipse. And you can convert those over to here, yeah, the a squared, and so on. And yeah, similarly, the vertical traces are also ellipses, and you'll get this one from, we'll just set the x equals to k, the first one. X equals to k. And then when you set x equals to k right here, if we just scroll up here, so x equals to k right here, move it around, you're going to get a, we'll go start from the original here. So y squared plus 9 plus z squared divided by 4 equals 1 minus k squared. So we're going to get y squared over 9 plus z squared over 4 equals 2, 1 minus k squared. And again, in this case, it's going to be an ellipse if we have k is going to be less than 1 or greater than -1, like that. So that this value here on the right side is going to be positive. Yeah, positive and not 0. And then similarly for this part right here, y equals to k, we're going to get a value such as x squared plus z squared over 4. And this equals 2, move over the y, it's going to be now 1 minus k squared over 9. And again, this is if k is less than, this is going to be 3 now, -3. Because we'll have 3 squared is 9, so that this has to be less than that. Alright, so let's graph all this out. So the figure below shows how drawing some traces indicates the shape of the surface. Alright, so let's take a look. What I'm going to do, I'm just going to draw the surface, and we'll just get straight to it, because it's hard to draw all in 3D or 3 dimensions. So what you're going to actually have is it's going to look like this, where it's going to be basically an ellipsoid, so elliptic figure like that. It'll look like this. Alright, and this is in 3D, and this part right here is the z-axis, and this goes all the way across here, and this is the y, and this is going to be the x. Yeah, it's going to look something like that. So let's write the equation again. So it's the x squared plus y squared over 9 plus z squared over 4 equals to 1. So let's look at it when we'll have when z is equals to 0. You're just going to have this part. Oops, when z equals 0, we're going to have this part. So then that means the a part is 1. So it's going to be right here, it's going to be 1. So at this point, it's going to be 1. And so it's an ellipse. So this is going to be 1, 0, 0. So because we're setting z equals to 0. And it's also, it's not just 1, it's going to be plus or minus 1, because it's the a squared there. It's the 1 squared. So then this at the back side is going to be the negative. So this is going to be -1, 0, 0. And similarly, at this point right here, this is where we'll have, this is the 9, like that. So that's going to be 3 squared. Let's leave it like that. So 3 squared is going to be, I'll just put that like this, 3 squared. And this becomes 2 squared. So this right here is going to be our 0, 3, 3, 0. Now 0, 3, 0. Like that. And then the backside is going to be the same thing, but -3. I'll just leave it like that. No, actually, I'll just ignore it. Okay, so it's going to be at the negative, and then the top one's going to be, and this is one is if you set any one of these to 0. So if you set if you set the x or the y to 0, you're going to have the z is going to be at 2. That's all just going to be ellipses. So anyway, we can see the ellipse right here. This one's the horizontal ellipse at z equals 0, and then this is the at x equals to, at y equals to 0. So set y equals to 0, you're going to have x squared plus z squared over 2 squared, and that's this part right here. It's going to be 0, 0, 2, and it's going to be an ellipse like this, vertical ellipse. Goes through, goes like that. So yes, epic stuff there. And then if you draw more ellipses, it's going to look something like this. And so the traces are just ellipses. And it keeps going on and on. So it looks something like that. Alright, so growing further, as always, we can graph this in a GeoGebra. So you can write it like this and we'll graph it out. Let's go to it. Oops. Right here. So we go over it right here. So hide this and show this one. So there's our, and I had the, zoom into the wrong thing. This is one like that. Yeah, that's one. This is going to be three. Yeah, so it's going to be a bit lopsided. If I can zoom in this part. So yeah, so it looks, that's the shape it is. Yeah, it's actually more vertical like that. Yeah, so if we go back to mine, this is way too wide. It should be shrunken over like this, because this is at 1, this is at 0, 0, 2 like that. And so here I just quickly copy and paste it from my calculus book just to get a better image. So this one, let's keep it there for the laugh. So here's a better image from my calculus book. So it looks like that. And that is much more in line with, this is the GeoGebra 3D graphing calculator. So yeah, that's a pretty cool shape. It's like a smooth rock. All right, let's go and let's continue further. So it's called an ellipsoid because all of its traces are ellipses. And notice that it is symmetric with respect to each coordinate plane. This is a reflection of the fact that its equation involves only even powers of x, y, and z. So that's pretty interesting. And this stems from, the idea of if you have it square, for example, it's all even powers. So if you're going to have an even power, if you're solving that equation for x squared, you're going to have x squared equals to, etc. I'll just call it, I'll say dot, dot, dot. Then if you take the square root of it, you're going to have a plus or minus dot, dot, dot. So plus or minus, and it's going to be, again, symmetric about it. Because you're going to have whatever answer, then you're going to have plus or minus. Same thing if you had a 4 to the 4 like that, and then if you take the cube root of it, it's going to be a 4th cubic root. You're also going to have a plus or minus setup. And here I just added both of them for completeness. And again, if you have to the 4 right here, if it's an even power, you're going to have, actually this is the 4. I got the 4th cube root. Basically, whatever number you have, if it's all minus, for example, 1 times minus 1 times minus 1 times minus 1, it's going to be positive because it'll be 4 of these, so they all cancel out, equals to greater than 0. Or if they're all positive, it's the same thing as if you had all positive. So it's the same thing. So again, even multiples of a negative is going to be positive. All right, and now this brings us to another example. So example 4, elliptic paraboloid. All right, so in this one we're asked, use traces to sketch the surface z equals 4x squared plus y squared, and so on. So if we put x equals 0 right here, so put x equals 0, we're just going to get z equals y squared. So the yz plane intersects the surface in a plane. Yeah, so this is the yz plane. So there's a y, there's a z. Intersects surface in a parabola like that. So if we put x equals to k, so put x equals to k, and we're going to get, and just move it over to the other side, we're going to get z equals y squared plus 4k. And this is still a parabola. This is just a constant. This just means that the parabola is going to be shifted. So this means that if we slice the graph with any plane parallel to the yz plane, and this one is at a shifted area around, so we obtain a parabola that opens upward. And I'll graph this all out, it'll make more sense. So similarly, if y equals k, the trace is, so this is just k, we're going to get z equals 4x squared plus k squared. Yeah, we'll get the traces is going to be z equals 4x squared plus k squared, which is again a parabola that opens upward. Again, this just means it's shifted and so on. And there's no negative, so it's just going to be basic parabola just going upwards like that. So if we put z equals k, we get, and now if this is z equals to k like that, so this will be k equals to, this is going to be k equals 4x squared plus y squared. So if we put z equals k, we get the horizontal traces 4x squared plus y squared equals k, which we recognize as a family of ellipses. Yeah, this is just going to be ellipses, because you could just move this over at the bottom, and as it's going to be, instead of writing 4, you can write it as x squared is 1 over 4. Yeah, divided by 1 over 4, and then you'll have the radius from that, and so on. And then this equals k, which we recognize as a family of ellipses, because again, you can divide k out into this, do that same thing, and have it equals to 1 there. So knowing the shapes of the traces, we can sketch the graph below. Yeah, so basically we just have a 3D parabola, all opening upwards and going up vertically along the z-axis. So we're going to have Something looks like this. I'll draw it more accurate this time. It looks like that, and then this goes up. This is going to be our Z, and then this is going to be dot 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 all the way to the bottom, and it's going to go like this, and that is our it's going to be our X. It's going to be our Y, like that, and this is going to be this is going to be our shape, but let's look at the traces there. So when we put in x equals 0, we're going to have a vertical plane that's going to be along this side, where x is always 0, so it's just along the y plane. So that means we're going to have, this is 0, we're going to have z equals y squared. So we're just going to have this exact line right here. This one exactly. This from here to here is exactly what we get. All right, so, and that's already in our shape there, so I'll just ignore that. And so the next one is right here. If we have, if x equals to k now, if we have x equals to k, well, before we even get that, this part right here is going to be at our z equals to, it's going to be z equals y squared and x equals 0. But then if we had another line across a plane like such that goes down like this one, we're going to get another parabola that opens up something like from that. It's going to open up all the way across this part right here. Yeah, so that is just a vertical slice in this parabola opening upwards, and there's this shifted away from the origin there based on this right here. When we plug in x equals to k, we get z squared equals y squared plus a squared. So we could write this down right here. Z equals to y squared plus 4k squared, like that. And in fact, 4k squared is just going to be this height there from here to here. That's all it is, because you're just going to add it. So it's going to be parabola, add it, and then shift it upwards. So that's pretty cool stuff. All right, going further. So the next setup is we'll have if we have y equals k, the trace is z equals 4x plus y squared. So now it's opening up in the y section. So you're going to be cutting it up this way here. So if we have y equals to k, so let's say we'll just do the basic one. So if we have if we have y equals 0, it's going to cut it across like from here to here. It's going to look something like this. It's going to go. I'll draw this like this. Yeah, let's draw it across like that in red, and then it's going to go dash 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 all the way across here, just behind that there. And this one is going to be our z equals to this is going to be z equals to 4x squared. Yeah, 4x squared and then plus k squared. Plus k squared, and this 4 like that. Yeah, that 4 indicates that it's not just going up vertically in the parabola, but not just that. But it's also timesing it by 4, so it's going even at a faster rate. So you'll have z is increasing by 4. Yeah, I mean, it's going to be increasing as in the parabola x squared, and then times it by 4. So it's, in other words, it's going to be going vertically up. It's going to be more shrunken inwards like that. All right, and lastly is when we have z equals k, we get horizontal traces. So 4x squared plus y squared equals k, just an ellipse. So if we have it at just a k part, we're going to get an ellipse. I'm going to draw it somewhere here. And then draw a dash line like that. It's going to look something like that. And that's going to be our ellipse. That's going to be at, this is going to be 4x squared plus y squared equals to k. Like that. And where z is equal to k. So that's our equation of that trace like that. It looks like that. All right, going further. So here's a more clear image from my calculus book, just to, because I got it this is scribbled a bunch of lines and so on, but anyways, it looks like this. There is our paraboloid. So now graphing in GeoGebra, plug it in as the same link, and we're gonna get this right here, z equals 4x squared plus y squared, and it looks just like this right here. And yes, this is more accurate than my previous one of the ellipsoid. All right, continuing further. So here's how it looks like. So you go above here. So you can go hide this, show this one here. There is our paraboloid or whatnot, right? So it looks pretty epic there, and it's squished at one end. So that's cool stuff. And let's continue further. So because of the elliptic and parabolic traces, the quadric surface z equals 4x squared plus y squared is called an elliptic paraboloid. So you have a parabolas going vertical, but then you have ellipses around here. So it's like a cone. All right, pretty cool stuff. So now continuing further, example 5. And this one is the hyperbolic paraboloid. So it says sketch the surface z equals y squared minus x squared. All right, so continuing further, so let's take a look at the solution. So the traces in the vertical planes x equals to k, so when you put in k, are the parabolas z equals y squared minus k squared, which open upward, but this just indicates they're shifted down, and then it goes above the origin there. So the traces in y equals k are the parabolas z equals, so when you have y equals to k like this, plug that in, so put the negative x in front. So we'll have z equals negative x squared plus y squared, which open up downwards. Yeah, which open downwards because of this negative there. So when you have x is positive, then the z is going to turn into negative going downwards. And this one shifts this up, and it's going to go down. So it's going to be shifted up and going down if this is the origin there, etc. And this other one is the opposite of that. Is going to go up like that, but it's going to be below the origin if k is a positive number. All right. So the horizontal traces is when z equals to k. So when z equals to k, just put it in k there. So we'll have y squared minus k squared minus x squared equals to k, a family of hyperbolas or hyperbolas. And we can see that from our conic sections. There's a hyperbola, so x squared divided by a squared minus. So there's that minus as opposed to the plus for the ellipse. So minus y squared divided by b squared equals 1. So epic stuff there. All right, going further, we can draw the family of traces below and show how the traces appear when placed in their correct plane. So this is going to be actually the hardest, most tedious one manually, but it's a pretty epic stuff what shows up. So for example, let's say the first one, so the first trace is the vertical ones, x equals k, and then we'll have this z equals y squared minus k squared. So if we have this in 2D, I'll go x equals to k, so we're going to get the traces z equals to y squared minus k squared. And then so if we draw this in 2D, if this is the z-axis and this is the y-axis, we're going to have, so at k equals 0, we just have a basic parabola. This is at, remember, the k just shifts it. So we're going to have z equals to, or just always just put k equals 0. And then at k equals 1, this just goes to the 1. So it's going to be just all parabolas, this k equals 1. And then shift this below, like this. We're just going to have another one, k equals 2, etc. Or k equals plus or minus 2. And yeah, this is because it's squared, because we have the square there, so it doesn't matter, it's always going to be the same value there, if you have plus or minus. And so now, if we do this in 3D, so this is the y equals k plane. Yeah, so in 3D, this is going to be the hardest part. So I'll just draw the z-axis and the y-axis here. And this is the x-axis. So we have to visualize everything in 3D. So let's draw the, this is at k equals to 0. So x equals to k, which equals to 0. And it's just going to be a basic parabola. And this is going to be on the zy plane. It's going to be just basically like that. So that is what we have right here. This is at k equals to 0. The k equals, yes, the x equals to k equals 0. So x equals to k equals 0. Now the next one, let's say we had plus or minus 1. So the first one's going to be plus here. So across this plane, we're going to have this right here is going to be below it. So instead of this, it's actually going to go, it's going to go 1 here. So 1. And then below 1. Yeah, and it's going to be, because 1 squared is it's going to be below. Like that. Yeah, so this is positive 1. Well, and I'll do is draw another line, make this extend this further. That's positive 1. This is going to be plus 1. This is going to be minus 1. And then we're going to subtract by that. This is the k. So then the parabola here is going to be below here. But this one, imagine this, you're looking at the 3D like directly from the x-axis. So now this is going to be below it. It's going to look something like this. This is going to be below all the way to 1. I'll draw this across here. This is going to be -1 because you're subtracting by 1. And it's going to be on both sides, so it's going to be -1 as well over here. It's going to look something like this. This goes through, and so on. Actually, what I'll do is I'll draw it in different color. I'll erase this, and I'll draw it in different color. Alright, so let's draw this in red. So that's this part here, and this part here. It's gonna go like it's gonna be, yeah, it's, again, you're drawing in 3D from an angle there, and this one here is gonna be k equals to -1, and this one is k equals to 1. So they're the exact same, but just shifted. K equals +1. So it looks like that. Yeah. So the peak is gonna be at the origin from the bottom part. It's gonna be so the bottom peaks or the bottom saddles or whatever these are called. It's the bottom there. Or the troughs, it's going to go higher and higher to the origin and go back down. So that's an indicator of how the shape's going to be. All right, so that was the x equals k, the vertical one. Now the next one, so the other one is the other vertical one is y equals k. So the parabolas, so when you have y equals to k, we're going to have z equals to -x squared and then plus y or k squared. So let's write that down. So we'll have y equals to k. So we're going to get z equals to -x squared plus k squared. So these ones are going downwards now. And this, let's draw this in the this is going to be, yeah, this is going to be our, so k is so that now we're going to have z, and now we're going to have the axis is going to be x. So before it was z and y, now it's going to be y, z and x because the other one's gone. And this is going to go, so when k is 0, that's going to be -x squared, so it's just going to go downwards like that. So this is k equals 0. And I'll put that inwards. K equals 0. The next one is going to be k equals to plus or minus 1. And so these goes upwards. So they start from up and then go down. And so on. This below it. I'll just go k equals 2 plus or minus 1. The next one is going to be like that. And this is going to be k equals 2 plus or minus 2, etc. Alright, so in 3D now, this is again interesting. Okay, so in 3D, this is going to be like this. This is going to be y, this is going to be z, this is going to be your x. So now we're going to be going, well, y is the one that's going to be the k, this is going to be changing. So at y equals to k equals 0, we just have the basic one going downwards, and it's going to go downwards on the z plane, so it's going to go like this. It's going to go down like that. I'll draw it like that. So that's how it looks like, and this one is at our k equals to 0, or y equals to k equals 0. So I'll just put that just for completeness. So y equals, just to make it easier to understand on my end. So y equals k equals 0. And then the next one is going to be, well, over here. This is going to be shifted up. So then this is going to be plus or minus 1. So let's go to the -1. It's going to go across here, -1. And then -1 is going to be higher up by 1. It's going to go downwards like that. So now, and I'll draw this in red as well. Alright, yeah, let's draw that in red. So it goes across here, and it's going to go like that. So that's the red. This one is at our k equals to -1. And then likewise, we're going to have exactly the same thing, but then now we're going to be shifted over to the 1 and 1. So it's going to be starting up above like that and going down like that. So yeah, going through that there. And this one is at our k equals to plus 1. Epic stuff. Yeah, and then somehow we have to combine all these together. So this one goes like that and goes down. This one, this side goes like this somehow. And yeah, and this one goes down and up like that on that side. Alright, so now the next one is the horizontal traces. That's going to be at z equals to k. We're going to have y squared minus k squared. So yes, equals to k. So we're going to have now the z equals to k, and now we're going to have our basic y equals x 2D graph. This is going to be now, let's see what it was again. So yeah, this is going to be y squared minus x squared equals to k. Y squared minus x squared equals to k, like that. All right, now this shape's gonna be this is a hyperbola. It's gonna look something like this. So if we recall a hyperbola, this is gonna be our x. So the distances, and this is gonna be the y minus x. This is gonna be actually a vertical hyperbola, and this is gonna be like this. So let's say we had k equals to 1. You can't have k equals to well, k equals to 0. If you have k equals 0, you're just gonna have 0 and 0. It's gonna be like this. Actually, no, you can have 0. So if it's equal to 0, so if we have, let's say if it's equal to 0, we're gonna get, we're just gonna get a straight line like this. So this is how it looks like if k equals 0. So k equals to 0 is here, and this is because, well, we're gonna get y squared minus x squared equals 0. In other words, we're gonna get y equals to x, and everything cancels out. So basically y equals x, and then plus or minus, if x is negative, it goes down, perfectly straight line like that. And then at this point is going to be our, so if we had, yeah, so this at this point now here, this is at k equals to plus, yeah, this is at k equals plus 1. Actually, not plus 1, just this is just at k equals to 1. And it's a hyperbola, so we get two shapes like this, like that. And this is k equals to 1, like that. And here I quickly teleported just to recap on that hyperbola. So it's divided by a right here. For this case, we have y squared minus. And it's since it's 1, these values are just going to be 1 there. All right, going all the way back down. So this is going to be 1 or 0, 1. This one here is going to be 0, negative 1, like that. And that's because it's y squared divided by a squared is, and a is just 1. 1 squared is 1. All right, so now graphing this in 3D. Now it gets next level. So we have it in 3D. Let's look how it looks like. It's going to be our z, and this is going to be our y. This is going to be our x, like that. And let's graph the k equals 0. That's just going to be our straight lines across it, like that, and like this. What is the y-x? So that's this is the y-axis. Rotate that around. So that's our k equals to 0, or z equals to k equals 0. Now when z equals to 1, draw this in red. All right, so draw it in red, and it's going to be a hyperbola on the top side. That is when you'll have a horizontal trace. So this is going to be at 1. Yeah, and that's going to be at 1, and it's the same thing. Then on the negative side, yeah, so then the other one is if you had a negative 1 here. All right, and now before we get further drawing this one, let's draw this part here. I forgot to do this one, and make this a bit nicer. It's supposed to be actually like an asymptote line to this section right here. It's supposed to actually go closer and closer to it. But anyways, it's close enough. I'll show the image of my calculus book for more clarity. So anyways, the next one is when we have k equals negative 1. So if k equals negative 1, this will be a negative 1, and then to make it positive, we'll move it over. This becomes positive, the y becomes negative, and we get a basic horizontal parabola. I'll just put it in like that. And it's going to look, yeah, it's going to look like this. And this is at our k equals to negative 1. This one is, I'll put there are the lines, k equals negative 1. And this value is going to be 1, 0, and likewise it's going to be pop like that. This is going to be at our negative 1, 0, like that. And again, at k equals negative 1, we're going to get a x squared minus y squared equals to 1. So it's switched up around because it's a negative sign there. Anyway, so we have that. So this is going to be, that's the y and that's the x opening up on the y side. That's the y. Now we're going to draw this in red. Draw this in red. And this is going to be at the this part right here, and this is going to opening up on the y. It's going to look something like this. It's going to be so hard to draw in 3D. It's going to look something like this, and it's opening up. That's 1. It's also distance 1. Be something like this, and then the other side, negative 1 on the y side. And this is going to be, yeah, extending out like that. It's going to be something like that. Like this. All right, and now this one is for the k equals +1, or the z equals k equals +1, and now, and this the bottom one is the z equals 0. That's this line across. And now what I'll do is, well, we got to draw now the. I'll do that in blue, but before we get to that, I'm going to extend this down. It's the z-axis and also the x-axis across that way. And now what we're needing to do is I'll draw this in blue, and this is for the k equals -1. So the k equals -1, that's going to be, well, it's going to go across, it's going to go down here, -1. And then it's going to go across, we got to go to the 1 on the x-axis. It's going to go ... all the way till the 1 here. And then we start here, now we open up along the x-axis on 3D. Picture that. Open up like that, or put it like this. Yeah, and then we go along on the backside. We go to the -1 here, go down, and it's going to open up this way, and so on. So again, it's very, very hard to do manually. And yeah, I'll show the calculus book image soon. But now, if we put this all together and see what happens. Or actually, we'll just show the calculus image right now. So for clarity, here are the graphs from my calculus book. So this is doing manually just to illustrate the process. But here's the calculus book right here. So traces in x equals k, r, z equals y squared minus k squared. So it opens up upwards like that. And then you'll have, and these are for different values of k across there. And then traces in y equals k, r, z equals to -x squared plus k squared. It goes down like that. And then traces in z equals to k are this right here. And note also when k equals to 0, you just get a straight lines across that. And then when traces in x equals to k, the vertical one, you're gonna get, yeah, I mean this one here, you put it down here, so it's exactly like what we had. Traces in x equals to k, like this goes, it goes down, then up, then down. And that's similar to what we had here. And then likewise for the traces in y equals k goes like this. It's like a saddle like that, and it goes this way here. So that's what we had. Then finally the advanced one, the hyperbolas, this right here. So traces in z equals to k, you have -1 at the bottom. This is the lines at the 0, and then you'll have the ones opening up on the y. This is for the k equals 1. That's this right here. So compare that with mine. It's very hard to say. This is, again, computer graphics there. So if we fit the traces, or fit together the traces, we can form the surface z equals y squared minus x squared, which is a hyperbolic paraboloid. All right, so let's try to do this all manually. So what's going to look like? It's going to look something like this. And then the shape. Yeah, the shape actually saddles down like this somehow, and then goes up, and it opens up like this, and so on. So it looks something like this, and this is the x-axis. This is the x, this is the origin there, this is the y, and this right here, I'll fix this up. Something like this actually, and it goes upwards like that, and so on, and then this goes out like that, y. This is dash dash, like that, and then this part right here goes down, dash dash dash, and then goes like this. This goes opens up like this. A curve, and then this goes like this, like that, 0, and you can see this is how the shape looks like. It's kind of like a saddle, and you can see that, well, we're gonna combine this all together. So if we combine this part right here, this is on the x-axis, going to go up and down. So we'll have this right here. Yeah, should be a bit lower. Yeah, so it should be a bit lower. So this and this is below, so it's hard to see without shading. But you're going to see this is going to be, we draw a trace like that. So there's our parabola at the bottom. That's actually this one right here at the bottom, and now we have the saddle on the top there. And then this one here is that one at the 0. Then at the bottom, it's going to go down, but they're all parabolas going like this. They're all going down, but this is below it, and then it's going down on the further side. And then now it's opening up at the lines like that. And the interesting part is this actually goes a line perfectly on that hyperboloid, so that those lines actually fit perfectly along it. And now this is expanding outwards and expanding like this, like a hyperbola, like that and that. So that's how it looks like. And yeah, now going further, so for clarity, here's the graph from my calculus book. So it looks like this. So much nicer than mine. Well, actually, mine's pretty good here. Yeah, it's pretty good. And yeah, it looks like that. And then if we graph this in GeoGebra, so plug this in, z equals y squared minus x squared, we get this this saddle like that. All right, let's open this up again. All right, so here we are right here, and there's our graph like that. You just hadn't showed. And yeah, it looks like the saddle. You could rotate it around, and it's pretty epic looking saddle there. It's actually what it's called as a nickname. All right, so that's pretty epic, and goes up, and you can zoom in, and so on. And yeah, that is quite fascinating. All right. And yes, so notice that the shape of the surface near the origin resembles that of a saddle. This surface will be investigated further in a future video when we discuss saddle points. Alright, and now let's continue further and look at example 6. And this is a hyperboloid of one sheet. So we're asked, sketch the surface x squared divided by 4 plus y squared minus z squared over 4 equals 1. Alright, so let's take a look at the solution. So the trace in any horizontal plane, z equals k, and is the ellipse. And this is going to be the ellipse right here. I'll put a colon. Like that is the ellipse x squared divided by 4 plus y squared. And then we convert the z into a k and then move it to the other side. Goes 1 minus z squared over 4. Actually, whoops, we moved it over, so it's going to be a plus, and this is a k. Yeah, my bad there. All right, so a k squared plus 4. And also, since we have a plus, we don't have to worry about setting k as less than any specific number, or less than 2 in this case. So going further, but the traces in the xz and yz planes are the hyperbola. So this is the ellipse. This is an equation of ellipse, so this will be a number. You can divide it out to get 1 there. So, but the traces in the xz and yz planes are the hyperbolas. And this one here, this is the xz, yz plane. Well, this is just set it to 0. So this is y equals to 0. Or actually, we'll go, actually, I will just do that. Calculus book does this first. So then if we put this y equals 0 there, we're going to get an x squared divided by 4. Then this 0 just vanishes. Then this is going to be a z squared over 4. Like this, yeah, z squared over 4 equals to 1. So this is a hyperbola because you have the minus sign. And also, if we have x equals to 0, we're going to get, this is going to vanish. We're just going to get a y squared minus z squared over 4 equals to 1. It's also hyperbola because we have this minus sign. Right, and this surface is called a hyperboloid of one sheet and is sketched below. So basically, in any horizontal plane, z equals k, we're going to get an ellipse. And then along the x, z, and yz planes, we're going to get hyperbola. So what does this shape look like? All right, well, if we graph this out, so the the horizontal plane is going to be an ellipse, and it's actually, the ellipse is going to be of this form. So this x squared over 2, remember the ellipse sign, this is going to indicate basically that radius there, the horizontal one. It's going to be 2, this one will be 1. So in other words, it's going to be shrunken more like this. It's going to be extending out to the x-axis more, like that. And we'll put it like this. This is the ellipse right there. We're going to extend this as the y. I mean, this is the z. Z like that. This goes all the way down here. And then it goes dot, dot, dot. And then what we're going to have is, and then along the xz and yz planes, these are these hyperbolas right there. This equals to 1, so it's going to extend that out to the 2 on the horizontal side. And then this one here is going to extend out to the 1 on the y side. So it's actually going to look like something like this. This is going to be a hyperbola. And this right here, it's going to be hyperbola on both sides, so it's going to go like that. And I'm going to draw this out like this. And yeah, just draw it out like this. and then this, like that. Then this goes around, like that, and then this goes dot dot dot, this goes dot dot dot, and this goes like that. Y, X, like that. And this point is going to be our 0, 1, 0, because this is the one underneath this one. And we could have a look at our hyperbola, just recap on the hyperbolas from the conic sections, and just scroll the way up here. This is a hyperbola like here. So this is the a squared on this side where you're subtracting from. Yeah, so if you have x squared, the a is going to be here. The y squared, if that's in front, and then the other one's negative, that's going to be where you're going to be at the b somewhere over here. So that's pretty epic stuff. So now let's continue, back here to our drawing. So we have that, and then this is going to be like that, and then this point right here on this x-axis this is going to be the 2. So that this is 1 in front. This one is the 1 in front for the 1. This one's going to be 2. It's going to be 2, 0, 0, 0, 0, like that. And yeah, it's basically going to be an ellipse everywhere. So this is how my drawing is. It's a bit off, but like that. All right, like that, and so on. And then on the other side, you're gonna have an ellipse, like, hyperbola, like that, going across, and so on. All right, it's gonna be something like that. This is hard to draw, and yeah. So here's the same image from my calculus book. Just make it a bit easier to see. So this was my drawing. That was the calculus book, so it's a bit nicer than mine. And you can see the hyperbolas on the this on the xz, and then you'll have the yz planes like that, and then you have the ellipses, all the horizontal ellipses everywhere. And then graphing in GeoGebra, we get this shape like here, which is pretty epic stuff here. This x-axis is this side here. Let's go and graph this out. Those are x squared over 4 plus y squared, and then I need to unhide this one. So this is our hyperbolic, and this is our elliptical paraboloid. What is that? This one called again? This one's a hyperboloid of one sheet. So that's pretty cool. So yeah, so the idea of using traces. Also, before we get to that, just zoom in more and show you some more stuff that looks absolutely amazing. All right. Alright, and now let's go to the next section. So this is on computer-drawn graphs of quadric surfaces. So the idea of using traces to draw a surface is employed in three-dimensional graphing software for computers, basically the one I've been playing around with. In most such software, traces in the vertical planes x equals k and y equals k are drawn for equally spaced values of k, and parts of the graph are eliminated using hidden line removal. And here I've just added a link to my earlier video that went over hidden line removal and so on in 3D software, so you can watch that video. So going further, so table 1 shows computer-drawn graphs of the 6 basic types of quadric surfaces in standard form. And all surfaces are symmetric with respect to the z-axis. If a quadric surface is symmetric about a different axis, its equation changes accordingly. So just shift things around and so on. So it's symmetric about the other axis. So this is what we have: x, y, and z. And there's the ellipsoid. The equation is going to be x squared over a squared plus y squared over b squared plus z squared equals. It is z squared divided by c squared equals 1. And all traces are ellipses. So notice the ellipses on this axis, and then going across that way as well, and then also horizontally as well. If a equals b equals c, the ellipsoid is a sphere. Then elliptic paraboloid. So it looks like that's an ellipse and it's an ellipse on the horizontal, and then vertically it's a paraboloid. So z divided by c equals x squared divided by a squared plus y squared equals b squared. And horizontal traces are ellipses. And then vertical traces are parabolas. And the variable raised to the first power indicates the axis of the paraboloid. And this one here, z is to the first power, so that's the axis. Going for the hyperbolic paraboloid, and it's that saddle one right there. It looks like that. There's all the traces on it. So again, this is how 3D drawing is usually made. So z over c equals x squared divided by a squared minus. This one's a plus, this one's a minus. y squared divided by b squared. And the horizontal traces are hyperbolas. So the horizontal one goes like this, and then on the other side. And then vertical traces are parabolas. So vertically you get a hyperbola, a parabola there, and parabola on any side you look at. Yeah, so if you cut it like this, you're gonna have let's see what kind of plane this. So you have parabolas. Actually, you have parabolas going down like this way, and if you look at it this way, you're gonna have parabolas going up like that, and then you have the hyperbolas going this way and that way. And then the case where c is less than 0 is illustrated. Yeah, so that's interesting. So c is less than 0 is negative there. All right. So then you're gonna have the y is positive when you move it over, and so on, and then the x will be negative. All right, going further, surface, the next one is a cone. So you have a cone looks like this, and then you have the equation z squared over c squared equals x squared divided by a squared plus y squared over b squared, and so on. And the difference is that this would be, both powers. This is going to be, z is going to be a power. Put a c squared as well, just for, make it similar to that. And then horizontal traces are ellipses. And yes, the horizontal, you're going to get an ellipse. Vertical traces in the planes x equals k and y equals k are hyperbolas. And yeah, these are vertical ones right here. And the x equals k and y equals k. If k is not equal to 0, yeah, so if you have vertical planes like this is going to be a hyperbola cutting it across there and there, there and there. Or you can have it the other side cutting it this way. You can also have there and there hyperbola. But if k is equal to 0, so you're looking at literally this point there, or this cut open there, then you want to get a hyperbola, but you'll get pairs of lines if k equals to 1. So in other words, it's going to go perfectly down like this. Yes, it's going to be a perfect line across there. So it's epic stuff. And then going further, so hyperboloid of one sheet, so over x squared over a squared plus y squared divided by b squared, and then you have a one minus there, z squared divided by c squared equals 1. And horizontal traces are ellipses, so the horizontal is always typically ellipse. Vertical traces are the hyperbolas, you can see them there, and at the bottom. The axis of symmetry corresponds to the variable whose coefficient is negative. So this is z, so then that's going to be the axis, this hyperboloid of one sheet. Now here's an interesting one, this is a hyperboloid of two sheets, this is 1, this is 2. And this hyperboloid of two sheets, this equation is negative x squared over a squared minus y squared over b squared plus z squared over c squared equals to 1. Compare that with the one sheet one. This one has basically 2 positives and 1 negative. This one has 2 negatives and 1 positive, so that's interesting. And then horizontal traces in z equals to k are ellipses if k is greater than c or k is less than negative c. Yeah, so that's interesting. So you're going to ellipse on the top and bottom if it's the absolute value is greater than c of k. So vertical traces are hyperbolas. So there's the vertical ones up and down, this way and so on. All right. And the 2 minus signs indicate 2 sheets. Interesting. And this one's 1 minus sign indicates 1 sheet. 2 is 2 and then 1. So hyperboloid of 1 sheet, hyperboloid of 2 sheets. Epic stuff. So now let's continue further and look at example 7. This is a hyperboloid of 2 sheets, as this one right here. So this one says identify and sketch the surface 4x squared minus y squared plus 2z squared plus 4 equals to 0. So dividing by 4, we got to get this in this standard form there. It's going to be a hyperboloid of 2 sheets. We first put the equation in standard form and see what happens. So let's put this all there. So we have this 4x squared minus y squared plus 2z squared plus 4 equals to 0. So what we'll do is divide everything by 4. Well, this right side is going to be just 0. It's still 0. And then this left side is going to be, well, this cancels, going to be an x squared minus y over 4. And then, divided by 4, just get rid of this right there. And this one's going to be 2 over 4 is going to be 1 over 2. This will be 2, and then it's going to be plus 1. Like that. And actually, we wanted to divide by negative 4. So we put it negative 4 instead, because we're going to move this over and we want a positive 1 there. So we'll put a negative. So this is going to be negative plus negative, and then this one's going to be negative 1, so we'll move it over to the other side, equals to 1. So negative 1, move it over, and we get that. So there is their standard form there. Now we have two negatives. We have a negative x squared, the negative z squared. This would be two negatives as well, but instead of but then the y ones will be positive. So it should be horizontal. This can be instead of this going up. So then this one would indicate that the axis is there. But since it's the y, then just by symmetry, it probably means it's going to open up like this. Yeah, it's going to open up like that somewhere. And then this is y is going to be the axis of this hyperboloid of two sheets. And so comparing this equation with the table 1, we see it represents a hyperboloid of two sheets. The only difference being that in this case, the axis of the hyperboloid is the y-axis. Is the y-axis, like that. All right, going further, so the traces in the x, y, and y, z planes are the hyperbolas. So if you have x, y, that's going to mean that's the horizontal one. So you have the x and the y. So that means the z is equal to 0. Yeah, so in other words, you're going to have z equals to 0. And then if you plug that in, you're just going to get a negative x squared over, actually not over anything, just negative x squared plus y squared over 4 equals to 1, because the z vanishes. And then for the y-z planes, that's going to be, let's look how the y-z would be. This is the y and the z. So in other words, we're going to have the x is 0. So this is going to be at our x equals to 0. This is going to be, well, this is going to be vanished. It's going to be y squared over 4, and then minus z squared. Z squared over 2 equals to 1. Like that. And so these are hyperbolas because there's just a negative sign there. So there's a negative sign and then a plus. Otherwise, it would have been an ellipse if they were both positive. Actually, if they were both positive, they would have been an ellipse. But since there's one negative and one negative, yeah, they're both hyperbolas. So going further, the surface has no trace in the xz plane, but traces in the vertical planes. Y equals k for absolute value of k is greater than 2 are the ellipses. And first, we'll illustrate that here. So this is the xz. So we have the x like this, z. So that means this plane right here. So that means the y is 0. So again, just basic stuff there. So y equals to 0. Or in this case, we'll show that first. We'll show the y equals k, then I'll show you why when y equals 0, you're not going to have it in this xz plane. But so when y equals to k, we're going to get negative x squared, and then this is going to be k squared, move it over to the other side. This one would be negative z squared. Negative z squared over 2, and then equals 2. This is going to be 1 minus k squared over 4. And what I'll do here now is just get rid of the just minus on these two left sides. I'm going to just minus by 1 on both sides. So what we're going to get is a x squared plus z squared over 2 equals to k squared, going to be positive, and then minus 1, like that. Yeah, so we have it like this. Yeah, and this is going to be, and these are going to be, they're going to be ellipses. So this is an equation of ellipse as we showed before, but we need k, the absolute value of k has to be greater than 4, otherwise it's going to be negative. I mean, absolute value of k has to be greater than 2, but k squared has to be greater than 4. Yeah, so I'll just write this down. So k... so k has to be greater than, this is, k is going to be, it's going to be greater than, or actually instead of that, just absolute value of k has to be greater than 2. And if k equals to 2, this is the right side is going to be 0, we're going to have a line and so on, and that's going to be trivial, so we'll just ignore that. And so there's no trace in in the xz plane. That's because again, if y equals k, or y equals k equals 0, you're gonna get, well, that's gonna be 0, so you're gonna have this negative 1 on this side. You're gonna have x squared plus z squared minus 2 equals negative 1. and this is positive, and this is negative. So this is less than 0, greater than 0, or greater than 0. So this is not a solution. And here I just wrote not a real solution, just because you could probably use real complex numbers or imaginary numbers to make that fit, but not real numbers. All right, going further. So the above equation, this one right here, can be rewritten as, so we just divide this all out over to this other side. So we're going to get, I'll just put this down here. So x squared plus z squared over 2 equals to k squared over 4 minus 1. So divide it out just to get it in the standard ellipse form. So divide this both out, or just divide this out on both sides, or just move it, just divide it out like that. And we're going to get x squared over k squared over 4 minus 1 plus z squared over 2k squared over 4 minus 1 equals to 1. So there's our ellipse in standard form, or almost standard form. We just got to get the square root somewhere there. But this is all right. And this is also for y equals k. So this is our equations. So we rewrite all that like that, and that's for the y equals k plane. All right, and these traces are used to make the sketch below, and so go back up here. So we have this sketch, we turn it over to this, and then the traces in the x, y, and then y, z planes are hyperbolas. So that's a key indicator, and that's these hyperbolas right here. And so this one's going to be the front one, this is going to be the 2. So at the z, we're going to have, at the y, we're going to have a 2. And then on this side right here, the y is also a 2. So this means a 2 squared. So this means we're going to have something that looks like this. I'll draw this. This is the z. This is the x, like that. And then this is going to be the y. I'll draw the y like this. And that's the y. And this is going to be at the 2, actually. This is going to be at the 2 and negative 2, just by our equation. This is going to be at 0, 2, 0. And this is going to be at 0, negative 2, 0. And we're going to get hyperbolas that extend outwards along that y-axis, because it's the positive one, and on both of the x and the z. This one is a 1. This one is a square root. It's going to be bigger than 1. So then it's actually opening up bigger on the vertical side than the horizontal, which is the one variable below it. So that's going to be something like this. Let's see if I can draw this out. It's going to be something like this, and this, and then these ones are all ellipses, like this side, on the vertical traces. So this is at the y equals k. So whenever you have a plane like this, y equals k, where k is greater than 2, the absolute value of k is greater than 2, you're going to get a hyperbola. But when it equals to 2, you're just going to get, you're going to get an equation of a line. And so you're going to get that point. But it's not going to be hyperbola. It's going to be 2 points or 2 lines. So what we'll do is that's what it looks like. And then also the horizontal. The horizontal is also going to be a, this is going to be a dashed line. Just like this, and this dot, dot, dot. And then this dot, 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 and this extends it out. This is y, this x. All right. This goes like that. And this opens up like this, and then draw the ellipse, dot, dot, dot. And this extends this out. All right, so something like that. And then there's the horizontal, this like this hyperbola. Yeah, so it looks something like that. And so again, those ellipses, the vertical one's going to be like this, that equation, something like that. And then graphing in GeoGebra, we're going to get something that looks like this. So that's exactly it. There's an equation 4x squared minus y squared plus 2z squared plus 4 equals 0, and it automatically converts it into this hyperboloid of 2 sheets. Let's go to the this one right here. Hide this, show this, and there's our shape. So that's pretty epic stuff there. Yeah, just play around with that. All right, continuing further. All right, and now let's take a look at example 8. This is dealing with an elliptic paraboloid. And so this one we're asked to classify the quadric surface x squared plus 2z squared minus 6x minus y plus 10 equals 0. So I already told the answer, but it's showing it how it is also difficult here. So by completing the square, we can rewrite this equation. So we're going to do some completing the square to get this in that standard or just more tangible form, because we have this x right here and the y. We want to get rid of those, and we can do that with completing the square. And in this case, there's no y squared, and there's no other variable besides there's no other separate variable besides x. So we can complete the square with x squared and x. And then we're going to have a y variable by itself, that's to the power of 1. And then the z squared is already to the power of 2 with no other variables. So by completing the square, we can rewrite this equation as, so I'll write this down with all of the relevant parts for the completing the square in front. So we'll have x squared, and then minus 6x plus 10, and then, so we just added this part in front just to make it easier. And then we're going to have plus 2z squared, and then minus y, or minus y, then the other part. Minus y, and then my plus 2z squared equals to 0. Or actually, better yet, because this is one variable, I'll move that over to the other side. So we're going to go plus 2z squared, move the y to the other side. So we're going to have equals to y, just because it's different from the others. So now we're going to complete the square. So I'll put CTS for completing the square. And recall my earlier, we had to do that. This just means, well, we want to get it in the form of this way. X minus a squared. And if you expand this out, you're going to get x minus a times it by x minus a. And then this is going to be, well, so x times x, then x times a. So we're going to have x squared. Then we're going to have a minus x times a. But then we'll also have another one here and here. So minus a times x again. So x times negative a, and then you have negative a times x, so it's going to be a 2. ax, and then we'll have negative a times negative a. It's going to be negative plus a squared. Negatives become positive. So plus a squared like that. Yeah, now if we compare it with this part right here, we're going to need, well, this part right here, negative 2a has to equal to this part. Because we have x squared minus 6x, and then this a squared, we can manipulate this, tend to get that like that. But this is the key one. So negative 6 has to equal to negative 2a. So in other words, we're going to have negative 6 negative 6 has to equal to negative 2a. So what we'll do is, well, this becomes positive, and then divide this out. Divide this out. You're just going to get a equals to 3. So negative 2 times 3 is negative 6. So that's what we have. And so that's a is 3, and also a squared is going to be this part equals to 9. So a squared equals to 9. So that means we could rewrite this as x squared. We'll just put this all out. So x squared negative 6x plus 9 to get the a squared, and then put a 1 like that here. So we split the 10 into 10 plus 1. And then we could also move it to the other side. We'll do that later. Plus 2z squared equals to y. And now what I'll do is, let's block this out, completing the square. Yeah, just block that out. Yeah, actually just put it for both sides. So we have that. And now this part right here, this is just this equals to x minus a squared, which equals to x minus 3 squared. So what we get is, we're going to get x minus a squared, or x minus 3 squared, and then put the 1 onto the other side, and we're going to get here 2z squared equals to y minus 1. And I'm just going to bold or circle this one like this. And yeah, so now comparing this equation with table 1, and here's I copied and pasted that part into here, we see that it represents an elliptical or elliptic paraboloid. So here's elliptic paraboloid equation. So we have z divided by c equals to x squared plus x squared divided by a squared plus y squared divided by b squared. And if we look at that right here, well, we have this x minus 3 squared, and then plus the 2z squared, and we have y minus 1. The only difference is instead of y squared, we'll have z squared, and then the y is there. So, and then right here we were told the variable rate. So the first part indicates the axis of the paraboloid. So this one's going to be actually along this axis here. But also, this is also shifted because we have this negative 3 there, and also y minus 1 is actually going to be shifted somewhere across here. And we'll illustrate that. And yeah, we can write this in this format. I'll just write it for completeness. And so what we're going to get is, I'll get this part right here. So x minus 3 squared plus 2z squared equals to y minus 1, and then just divide it out by 2, and just divide everything by 2. We're going to get x minus 3 squared over 2 plus z squared over 1. And yeah, for completeness, we'll just put a square root 2 over 2. Like that. That's just 2. And this one's just going to be 1 squared. And this equals to y minus 1 in bracket, indicating it's shifted. And this is going to be divided by 2. So square root 2 over, actually this one's just c, so we don't need to do that. Divided by 2. Yeah, so that is our standard form. That's our standard form like that. And yeah, it's going to be like that, but shifted. So it's shifted by this negative 3. And this one is the z part's not shifted, so it's going to be on the xy plane. And this is y equals 1 shifted by 1, shifted by 3. And here I stated that, so here, however, the axis of the paraboloid is parallel to the y-axis, and it has been shifted so that its vertex is the point 3, 1, 0. And when you have this minus there, so basically it says to get to x equals 0, you need to put x equals 3. So you basically is shifting everything. And to get to y equals 0, you need to put y equals 1. And then the z is not shifted, so it's 0. And the traces in the plane y equals k for k is greater than 1 are the ellipses. So here, let's just put the plane y equals k. So this is going to be the vertical plane. This is going to get x minus 3 squared over, or just ignore that. We'll just go back to how it looked like. So this is simpler, x minus 3 squared, and then plus 2z squared. 2z squared equals 2, and this is going to be k minus 1. Like that. And again, these are ellipses if, the only way we get ellipses if this is going to be positive, because then we get divided out. So then k is going to be greater than 1. K is greater than 1, so then, for example, 2 minus 1 is 1, 3 minus 1 is 2, etc. So k is greater than 1. If k is greater than 1, like that. All right, going further, the traces in the xy plane and the x equals 3 plane are the parabolas with equations, and recall the xy plane. So if you have an x like this is y, so that means this plane, so that's the z equals 0 plane. So we'll put z equals 0. So z equals to 0. We're going to get, well, this part vanishes, and this is the y. We'll move it over the one on the other side. So what we'll actually get is y equals to x minus 3 squared plus 1. This is a parabola, and it's shifted up, and it's shifted to the on the y-axis by 1, and then it's also going to be opening positive sign on the y-axis. And then the x equals 3 plane, the reason is that because this is shifted. So if x equals to 3, we're going to get, this vanishes to 0, so we can't just put 0, 1 vanish. And then the next one, this is going to be similarly, y equals to, move the 1 over, this is going to be 2z squared plus 1. So again, shifted there, this is on the vertical side there. So vertical parabola, this is the z, and this is the horizontal parabola. Again, all shifted by 1 there, and this is shifted also the 3 on the x-axis. And we can see that because this is the x equals 3 plane there. Alright, so now going further, we can draw this out. So the paraboloid is sketched in the figure below. So it's going to be shifted over to the 3, 1, 0. what I'll do is I'll put this down here, 3, 1, 0, and it's going to look something like this. It's going to have, it's going to open up like this, and it's going to have axis like that. I mean, it's going to be horizontal parabolas on the z equals 0 plane, and then the vertical parabolas on the x equals 3 plane. So we're going to go, this is going to be up to 1, and this is going to be the x. This is 3. This is 1. Yeah, this is going to be 3. And then this part is the, keep it going like that. This is the y, and this is the z, like that. And what I'll do is I'll shift this down a bit, so we can have a better, a better z axis. So z is like that, and yeah, that's 3. This is going to be 1. Yeah, so shift it, and it opens up like that. So that's pretty cool stuff there. And this, because it's, yeah, 3D like that. And this is a y. Yes, that's pretty cool stuff. And now, yeah, if you just graph a GeoGebra, we're going to get this part right here. So there's our equation: x squared plus 2z squared minus 6x minus y plus 10. It automatically does everything, and it graphs it like that. And we can have a look at it. So unhide this one, show this equation. There is our, this is a paraboloid. Yeah, or more specifically the elliptic paraboloid. So yeah, that was the name. So the elliptic paraboloid, and yeah, that's pretty epic stuff there. All right, continuing now further, the next section is going to be, we'll discuss briefly on the applications. So applications of quadric surfaces. Examples of quadric surfaces can be found in the world around us. In fact, the world itself is a good example. Although the Earth is commonly modeled as a sphere, a more accurate model is an ellipsoid because the Earth's rotation has caused a flattening at the poles. See exercise 1. Circular paraboloids obtained by rotating a parabola about its axis are used to collect and reflect light, sound, and radio and television signals. In a radio telescope, for instance, signals from distant stars strike the bowl are reflected to the receiver at the focus and are therefore amplified. So you have light coming across anywhere here, it's going to go always to the focus. Goes here, goes straight to the focus of this parabola. So that's pretty cool stuff here. It goes like this. Focus is also there. No, actually, ignore that part. It's not going to be this one. No, it has to be parallel. So if it's parallel with it, then it will strike it. Yeah, but if it's going like this, yeah, because you could obviously put it here and it'll just go back like that. But it will focus the parallel rays. So the idea is explained in my earlier video, which is briefly explained below. I'll go over it a bit here. So basically, in that video, my earlier video, I showed that when it goes parallel like this, you have an angle beta and this angle alpha, and I showed that the angles are the same when it's parallel. So the angles from the focus of any point on the parabola equal each other. So any point right here, this angle, this is going to be theta, this is going to be beta. So these angles always equal each other. So that's pretty cool stuff. And hence all you do is hit it, and it will go back straight to that same angle. And yeah, so this is going to be, and this is shape of it. So paraboloids are used as the shape of some automobile headlights and mirrors for telescopes. So you could also shine the light from the inside here, and then it will reflect accordingly. Yeah, so you can have the light source, and it goes anywhere it goes here, it will go parallel to it. So you have a light bulb. So here's dark oncoming driver's eyes. Yeah, this is oncoming driver's eyes. Light road ahead, and yeah, this is dispersed light. Now you have a lens to make it focus downwards. And yeah, there's a reflector, and that's a parabolic reflector. There's the high beam filament, if present, culminated light. I believe that's straight light. Yeah, that's just traveling parallel to each other. And yeah, so this shines down to the road, so you see the road, and it's darker on the top. We're going further. Here is the primary mirror is parabolic. This is a telescope, reflecting the parallel rays to the focus. The secondary flat mirror redirects this towards the eyepiece. So you'll have light coming from the parallel light coming from celestial body. When you're looking at a telescope, it hits this parabolic mirror, and then focuses it on the focus, which is somewhere probably around here or whatnot. And then, but there's a secondary mirror. It bounces off and goes into your eye. So you could So you could focus distant light into a small area so you could see it zoomed in. So that's pretty cool. Alright, going further, the same principle applies to microphones and satellite dishes in the shape of paraboloids. So you'll have a camera like this, and there's a microphone, and so on. This is gonna, the sound comes here, it's gonna focus all over there, and you're gonna record it amplified. And then so the parabolic microphone. So there's the sound. The sound vibrates, goes in, and you focus it all towards this. It's more amplified. And there's also satellite dish. Also reflects signals to the focus of a paraboloid. So the light or radio frequencies or electromagnetic frequencies goes here and it goes straight there. That's pretty cool stuff. And going further, cooling towers for nuclear reactors are usually designed in the shape of hyperboloids of one sheet for reasons of structural stability. So there's the hyperbolas on this axis, and then you're going to have the ellipse on the horizontal. That's pretty cool stuff there, of one sheet. So you have just one sheet like that. And there's the nuclear reactors. So nuclear reactors have cooling towers in the shape of hyperboloids, or hyperboloids. And then pairs of hyperboloids are used to transmit rotational motion between skew axes, or basically lines that never intersect each other. Right? So these lines right here never intersect each other, and they're below it. So this goes like this. So it never intersects each other. And that's the skew lines. So the cogs of the gears are the generating lines of the hyperboloids. And so you're going to have a hyperboloid right here, and made of all bunch of straight lines across in an angle like that. And then these transmit rotational motion between skew axes. So this is going to rotate around it. This rotates, so that'll be pretty cool actually seeing that. Yeah, so actually here what I've done is I put a link to a YouTube video that just shows how these are in operation. So here's an example of it. I'll just mute it and we'll show it. See, there it is. So there it is rotating. I'll make it faster speed. That's pretty cool stuff. So you have two shafts there, and it can transmit rotational motion, and then you'll have, yeah, so you can transmit rotational motion across those two axes like that. So you have two close by each other. So that's pretty coll stuff. So hyperboloids produce gear transmission. Yeah, so that's pretty cool stuff, and that's something I should explore in a future video possibly. We're going further. So exercises. So exercise 1, modeling Earth as an ellipsoid. So traditionally, the Earth's surface has been modeled as a sphere, but the World Geodetic System of 1984, or WGS-84, uses an ellipsoid as a more accurate model. It places the center of the Earth as the origin, and the North Pole on the positive y-axis. The distance from the center to the poles is 6,356.523 kilometers, and the distance to a point on the equator is 6378137 kilometers. All right, so this question has multiple parts, and yeah, the first part is part A. Find an equation of the Earth's surface as used by WGS 84, or the World Geodetic System of 1984. And then part B says curves of equal latitude are traces in the planes z equals to k. And what is the shape of these curves? And then last part C, meridians or curves of equal longitude are traces in the planes of the form y equals mx. So we have a line like that. What is the shape of these meridians? And then, yeah, so let's just jump right in. So solution to part A, Earth's ellipsoid equation. So recall the equation of an ellipsoid. So, because we want an ellipsoid equation, this one from table 1. So x squared divided by a squared plus y squared over b squared plus z squared over c squared equals 1. And all traces are ellipses, and if a equals b equals c, the ellipsoid is a sphere. So we got to write it like that. So let's draw the shape of the Earth in 3D. And we know the basically the axis points, or the at the x-axis, at the y, and at the z and the y, based on the number c, a, b, c, like that. And also we know that the distance right here. So place the center of the Earth at the origin, and the North Pole is the z-axis. So then the distance from the center of the poles, from the center to the poles, the north and south, is going to be 6,356.23, and the distance to a point on the equator is 6,378, like that. And I'm going to do is actually, yeah, we'll just write it down. Anyways, so what this means is we're going to have a flattened ellipsoid. It's going to look something like this. Just draw it a blob like that. And now this is going to be, at this point, this is the x, this is the y, and that's the z, like that. So then this is the y, And at this point right here, this is going to be, well, 0 is x, and then this is going to be the same for the x one. It's going to be 6378.1370, like that. And let's just see what it was. Yeah, 6378. This is to the equator, and then this one right here, 6356.5.23. That's going to be at this vertical part. So this is going to be 0, 0, 6, 2, 5, 3 point. No, actually, this is a 6 right here. 6, then 0.523, like that. And if you go back up here, yeah, 6356.523 and 6378137. And then at the equator, so any point here, this is also the equator. This is going to be this is also going to be the same as this y1, but the x-axis. So 6378.137, and then 0, and then 0, like that. And then if you trace this around, it's just going to be like that, dot, 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 go all the way across, like this, and so on. And then this is going down like this to the center of the Earth. That's the origin. So it looks something like that. Yeah, so that's how the Earth looks like. And now to plug these in, because we know that these values, just throw that in there. So this one will be C, and this A and B are the same. So recall that the parameters A, B, and C of an ellipsoid represent the distance from the center to the edge of the ellipsoid along the x, y, and z axis, respectively. Thus we have the equation of the ellipsoid. Yeah, thus the equation of the ellipsoid is as follows, and that's going to be x squared over a, which is going to be 6378.137, like this, squared, make this neater, and then this is going to be plus y, it's going to be the same thing, 6378.137 squared, plus z squared equals to, this is going to be 6356.523 squared equals to 1. Alright, yeah, so that's our equation of the Earth as an ellipsoid. So graphing in GeoGebra, so we'll graph that out. So note first that we have to zoom out a lot to see the Earth, because we're dealing with 6,000 plus kilometers there. So note that we have to zoom out to see a lot to see the Earth. So what I did was here, wrote the point 6378 and 137, it rounds up as that's this point, and there's this point right here is, that's the first point A. Point B is the y-axis, and then we have the 6356. And it lines up right on this sphere that we added over here. So let's go over it to it. So this was right here. And so we're going to have the Earth. Yeah, so notice that if I show it, it's not showing because I need to zoom out a whole lot. So we're going to zoom out. So notice, this shows the scale of the Earth. So there's the axis, all 1, 2, 3. I got to keep going out until we see it. So this is 100 kilometers, 120, 140, still going. So we're in the 400 range, 1,000, there's the Earth. So yes, absolutely massive. Alright, there it is, and all the points match up exactly on this sphere, and there is our equation that we put in right there. That is epic stuff there. That's the Earth. Alright, let's continue further. So let's look at the solution to part B. And part B asked, curves of equal latitude are traces in the planes z equals k, and that's the horizontal. What is the shape of these curves? Well, if we cut it equal latitude, cut it at z equals k, we're going to get circles, actually. So parallels or circular lines of equal latitude, so solution to part B. So note that latitude is the vertical angle, we'll call this theta, and longitude, or phi, we'll call that phi. This is the vertical angle phi in this case, and longitude is the horizontal angle, this is lambda, from the center of the Earth. So if it's equal latitude, it's going to be a giant circle like that. And then this is lambda, this is this angle from here to here. Yeah, so then if we're going to have the same angle everywhere across here to here, that's going to be these lines there, those are the meridians, and that's going to be the ellipse, the whole vertical ellipse. So horizontal circles and a vertical ellipse, and we'll see that. So we can determine the curves of equal latitude by setting z equals k and finding the traces. So we have this equation, put z equals k and find the traces, and so let's just put that in. So we're going to get, z equals to k, and then we're going to get x squared over, this is just going to be 6378.137 squared plus y squared 6378.137 squared, and then this equals to, and move that over, so we're going to have 1 minus k squared over the 6356. So it's about 22, about 22 kilometers more squished than the equator. Alright, so this is going to be 523. Yeah, that's right, squared. So that's our equation. And this is for k is going to be, well, the absolute value of k is less than, just going to be less than 6356523. So that this right here is going to be positive. So it's less than is always going to be positive. In other words, we're going to get a circle everywhere. And so these traces are horizontal circles since the horizontal radii are identical. So there's A and B, they're identical. And that's going to be our radius R. We can move it over to the other side. And this one, depending on the value, we could divide it out and then move it over and get the radius, which is going to be shifting. So graphing in GeoGebra. So note there's some interesting stuff here. You can't just draw a circle in GeoGebra using these equations, because you're going to get actually a cone. So graphing in GeoGebra. So we have this set up right here. So I put this, and I also put k like this, and then z equals to k, and then I shifted it. So there's the equation, and I shifted it and see what happens. So let's go over it, to it. So I'm going to go, so we have A, B, C. Just remove those over. We can keep them. Not a big deal. Now we have k, and then actually k we don't need to draw it. All right. So now the issue is if you plug this in, you're going to get a cone because it's in 3D, and this graphing calculator, I can't put in the z equals k into it. So if I hide the Earth, so we get a cone like that. So we just get a flat cone like that corresponds. Yeah, so you could zoom in like that and go in. And but so what's more important is actually just the z equals k, and I'll show you the other part. So you move this down, you're going to get circles everywhere. So that's shrink. So notice the trace, you can see that visually. So you can see visually is just a circle. And then the k value go down, so put this plane down, and you're going to get a circle like that. So that's pretty cool stuff. And then this cone corresponds to that circle there. But it's a cone in 3D, because I don't know how to put a z equals k into the equation directly. But anyway, so I put a note there. So to graph the 2D circles, we need to use the Desmo's 2D graphing calculator, or you could use GeoGebra as well. And actually, no, the GeoGebra. We need to use the GeoGebra. Yeah, GeoGebra has this setup here. So if you go here, and then so the exact same equation, and now we'll have k equals 0, and now this is going to be our k there. Let's go here. I don't know why there's a 0 there. Well, actually, that's because it's set to it. I think it's set to it. Yeah, k equals 0. Yeah, so that's the k equals 0, and that's going to be at the equator. And notice what happens here. So shrink it, goes bigger, shrink it. And this corresponds to these setups right here. So notice how as k gets bigger, you're going to get a smaller circle. So as k gets bigger, you get a smaller circle, this until you get the equator. And then you go below it, so there's the equator, and then it goes back down. So that's pretty cool stuff. And there is our equation like that. And this is in 2D. Otherwise, you're going to get a cone. So that is quite amazing stuff. So, and again, note that changing the k value makes the circles smaller or bigger as they would appear in 3D, viewing vertically away from the pole. So just straight on top or below. All right, that's pretty epic stuff. So now let's take a look at the solution to part C. And this is meridians or elliptical lines of equal longitude. And we'll go and look at the actual question. So this is part C. So meridians, curves of equal longitude, are traces in the planes of the form y equals mx. what is the shape of these meridians? So let's write that down then. So it's going to be y equals mx. So the meridians or lines of equal longitude can be determined by setting y equals mx and finding the traces. Yeah, so if we do that, we'll just put y equals mx. And then this means that we're going to have x squared over the usual, just put the big giant number, 6378.137 squared. And then plus, well, the y is going to be mx, so that's just going to be, let's put it for, I'll just square. So this will be our y. It's going to be mx squared. This is our y. This is going to be our my squared. I mean mx squared, which is our y. Like that. Alright, so we have that, and then this is going to be divided by, and it's the same thing, 6378.137, and then squared. And then this is going to be plus the z1, going to be 6356.523 squared equals to 1. Alright, so now what we can do is, well, we could factor out the like terms. Basically, we're going to have this whole part, this x squared over the radius, and factor that out. So we're going to get, and then factor, we're going to get a 1 on this side is just 1, and then plus m squared. And we're going to get an x squared over 6378.137 squared, and then plus, this is just going to be an ellipse, z squared 56.523 equals 1. So this is an ellipse, and that's because, well, these aren't going to be, these aren't the same, and also this is going to be changing based on whatever this m value is. So it's an ellipse that's variable, depending on the m value. Alright, and yeah, so these traces are vertical ellipses, because this is a z squared, so basically y equals mx plane, which is a vertical plane. Since the horizontal and vertical radii are different, I just call them that. So this, the horizontal is going to be different, there's going to be also further adjusted by this, and then this one here is different. And then graphing in GeoGebra, what we're going to get is, so we'll have this here, and so another issue is if we just plug that in, we're not going to get, I forgot the shape here, but I think it's going to be possibly, yeah, it's going to be a horizontal cone actually. And the mx, what it actually just does is shifts the, it goes in a circle, so it shifts the plane across it. So instead of going like this, y equals mx, so y equals 1 is going to be flat, and then if m is 1, it's going to be perfectly 45 degree. But if m is, let's say, 10, it's going to go more directly here. If it's 0, I think it's going to be, yeah, y is going to, the x is going to increase more, the y is going to increase less. That's going to look like. And you can have also negative as well to flip it, and we'll show that soon. So we have this, and it looks like this. You have the y equals mx plane. So this is the y equals mx plane. And then it cuts it straight through. You're going to get these vertical ellipses. So that's pretty epic stuff. So let's go and do that. And there's a y equals mx. And there's our 1 plus m x squared over 6378.137, rounds up 1,4, and so on, our ellipse. So going here, let's go, we have to go to here. And to do this, we're going to hide this one. Now we're going to deal with, so if I plug this in, yeah, this is going to be we already had the vertical cone. So the next one's going to be y equals mx. Yeah, so here, if we plug this in, it's going to be actually an ellipse that's like shaped like that. Because it's, yeah, it's going to be shaped like that. Let's see how this looks based on the values. Whoops. M value. Actually, yeah, it's going to be like 2 lines there across. Yeah, I'm not exactly sure how what's doing on the, yeah, it's going to be, let's see here. Yeah, it's going to be a elliptical cone that's horizontal. And again, it depends on the shape. That's where you can have weird ellipses. If you're looking at it like this, you're going to see a shape like that. But what I'm going to do is I'm going to hide this 3D one. So show it here. So this is, and then zoom out. So this is a y equals mx plane. If you move this, it just rotates around. So notice it's rotating around. You're always going to get an ellipse. But if you look at it from one side only, that's why this is a bit issue. So if we look at it straight from here, and then show this cone, let's see this one right here, what does that look like? Whoops, yeah, there it is, this one here. Yeah, that's straight through like that. It's going to be an ellipse on this side. But anyways, similar to the other one, we're going to have to graph that in 2D. Alright, so going further. So note that we have to graph with Desmos 2D graphing calculator to obtain the 2D traces. Note also that I had to change Z to a Y for Desmos. This one, yeah, just pretend this is a Z, because you can't just put a Z there in Desmos, because it's 2D. So pretend that's a Z, and it's going to look like this. And we'll show you what that shape is actually doing. So we go here. Now plug in M here. Oh, actually, we don't need M. Oh, we actually do a slider there. That's cool. Yeah. So this shape like that, then until it gets to perfectly flat, because you're rotating that M. And then this one. I think it goes it expands here. How does it go? Negative. Okay. Yeah. There's a specific value you can't go beyond. So this is the most. And then goes like this. 2D, and until it flips over to the other side. And that's again looking at it from here. This is just looking at it from an angle like that. So that's what it's graphing, like directly head on, and so on. And has some other issues there. Anyways, that's pretty epic stuff. So note also that changing the M value makes the vertical ellipses as one would see it, looking horizontally at the Earth towards the equator. So looking directly at it. And then if you rotate that line, you're going to have those ellipses form accordingly. Anyways, going further, and now let's take a look at exercise 2. And this is a hyperbolic paraboloid generated from lines. And we're asked, show that if the point ABC lies on the hyperbolic paraboloid z equals y squared minus x squared, then the lines with parametric equations x equals a plus t, y equals b plus t, and z equals z plus 2 times b minus a t. Yeah, and the other line, x equals a plus t, same thing, y equals b minus t, so there's minus there instead. And then z equals c minus 2 the times b plus a times t. Both lie entirely on this paraboloid. In other words, we can make a paraboloid using 2 lines. This shows that the hyperbolic paraboloid is what is called a ruled surface. That is, it can be generated by the motion of a straight line. In fact, this exercise shows that through each point of the paraboloid, hyperbolic paraboloid, there are 2 generating lines. The only other quadric surfaces that are ruled surfaces are cylinders, cones, and hyperboloids of one sheet. And this is the one that was actually the hyperboloid gears. If we go back here to the applications, and that's this one here. This is of one sheet, and these are all made of straight lines. So that's pretty epic stuff. And then you can do rotation there and gears and so on. So you get yeah, that'd be pretty epic. I want to learn more about that. Anyways, going further, so let's take a look at this. Show that this hyperboloid. So again, there's a minus sign. It's the hyperbolic paraboloid. It's a minus sign, and then this is z is 1 by itself. So let's take a look at that. So solution, recall, and show that these lines all coincide on it. So recall the equation of a hyperbolic paraboloid. It looks like that saddle. So you have z over c equals x squared minus divided by a squared minus y squared divided by b squared. And horizontal traces are hyperbolas. Vertical traces are parabolas. So the horizontal ones are hyperbolas. So this one, horizontal, horizontal, horizontal on the other side. Like that, those are hyperbolas. And then the vertical ones, if you cut it anywhere, it's going to be a parabola. It's going to be parabola, parabola, and then also a parabola on this other axis. That's cool stuff. And the case where c is less than 0 is illustrated. It looks like that. And yeah, so if c is less than 0, then this negative is going to be here. So y is going to be positive and x is going to be negative. And that's actually similar to ours. So this is going to look just like ours then. So this will be a similar R shape where c is less than 0. If c is positive, you're going to have x there. It's going to be shifted around where the top part's expanding on this side, the bottom part's expanding on the other side. Anyways, so recall the parametric equations of a line. Just to recall it. So, because we're given parametric equations, it's right here. X plus at, y equals that. So recall what they were from my earlier video. Here's a link to it. Here's a thumbnail. Pretty much explains what it is. So here's in vector form, r equals r naught plus t, and then the parallel vector. So this is the equation. This r is the line, equals to r naught, the starting vector, plus the variable t, times it by this parallel vector. And it goes across there, like that. And that's the equation of a line. And you can write this as, in this bracket form, meaning a vector, x, y, z. So just point on there, x, y, z. And you can also break it up into its components. So x0, y0, z0, a vector plus t times a plus b plus c. And then you can add these up, these vectors. So x naught plus ta plus y naught plus tb plus, and then the next one z naught plus tc as a vector. And then you can separate these and you get these parametric equations. So x equals x naught plus at, y equals y naught plus bt, z equals z naught plus ct. So that's our parametric equations. Alright, so let's plug in the first set of parametric equations of a line into the given equation of a hyperbolic paraboloid. So we go back up to our equations. Hyperbolic paraboloid z equals y squared minus x squared. Then you have the parametric equations x a plus t, b plus t, and then this one's z c plus 2 bat. Alright, so we have z equals to y squared minus x squared, like that. And also note that we know that a, b, c are on it. So we're given that point A, B, C lies on this. So in other words, we can just plug all those inside and they should all equal. In other words, we should have C equals to, well, this is y, so it's going to be b squared minus a squared. Like that. So because A, B, C are on this hyperbolic paraboloid. Alright, so now let's get our line. Our line is going to be x equals to a plus t. Then we have y is equal to b plus t. B plus t, and then z is equal to c plus 2b minus a t. Alright, so now let's put these in together. So we're going to get z is going to be c plus 2b minus a t equals 2, and then x is, y is first, so b plus t squared. Minus x is going to be a plus t squared. And now we could just expand these ones out. That's just going to be simply, b squared plus, and then b times t twice, 2bt. And then minus, the plus here for the next one, plus t squared. The next one here now is the same thing, but there's a negative everywhere. There's a negative sign. So we're going to have a squared, and then a times t twice, minus 2at, and then minus t squared. Alright, now we close this off. We're going to get, those cancel, and now we're going to get a b squared. There's a minus there, a squared. And also look at the like terms of this one, 2 and 2t. So we can remove that out. We're going to remove 2 and t. I'll put that at t soon. We're going to get b minus a. T. In other words, and then bring this down, this is going to be equals to c plus 2b minus a t. Now this cancels. This cancels. So we're left with c is equal to b squared minus a squared. And that's exactly the point on the hyperbolic paraboloid. So there it is, c equals b squared minus a squared. And so going further, so since the point ABC is on the hyperbolic paraboloid, then the line is also on it. Yeah, so this is on it. So this means this whole line is on that hyperbolic paraboloid at all times. So similarly, for the other set of parametric equations we get, and let's see the only difference between it. So a plus t and then b minus t, and then we'll have this the c minus 2, and then there's a plus a there. All right, so let's write down what we get here. So we get our z is equal to y squared minus x squared. And then similarly, again, we have our point on our curve, x, b squared, a squared. And then our line is going to be x equals to a plus t. Y is going to be different. Y equals b minus t. B minus t. And then z is equal to, this is going to be c minus 2b plus a t. So the minus is switch. So remember, this was a plus, then a minus. Now we're going to get a minus and a plus. All right. And then let's do that. So again, it'd be very similar to the other setup. And then put those inside. So we're going to get a c minus 2b plus a t is equal to, and then this is going to be y squared. It's going to be b minus t squared minus x, which is a plus t squared. like this. This equals to b squared is going to be multiply this out, b squared. Now this is a multiplied twice, it's going to be negative 2bt, and then a negative t times negative t is going to be plus t squared. Now the next part here is going to be negative everywhere. Let's go a squared, and then a times t twice, minus 2at, and then minus t squared. All right. Like this, cancel. This equals to b squared minus a squared. And then, that's b squared minus a squared. And then take out the like terms. And the like terms are going to be the negative 2 and t, and negative 2 and t. So we'll take out the negative 2. This becomes positive b plus a, and there's a t that we took out. And this is going to be c minus 2b plus a t. Let's bring that down. We'll put it like this. Bring it down. This cancels. This cancels. And again, same thing. We get c is equal to b squared minus a squared. So this line is also on the hyperbolic paraboloid. So that's epic stuff there. Thus, we have two sets of lines on the hyperbolic paraboloid. And writing the lines in vector form, we can then plot them with GeoGebra. So let's recap quickly on that. So we have the lines are given in a parametric equation, so we just got to go backwards and then write them out like this. Here, so basically a point on it here, and then plus t times, and then plus t times just a parallel vector in there. All right, so let's go further and let's write this down. So first, let's write our equation: z equals y squared minus x squared. That's our hyperbolic paraboloid. So let's go line 1. This one is for this. Here's the parametric equations: x equals a plus t, and then we had y equals b plus t, and then z is equal to c plus z plus 2b minus a t. All right, and then basically writing this in vector form, we'll call this r1. This equals to, this is going to be a point on it, so that's going to be point A, B, in vector form, C, and then we basically separated everything, take the t out. This is going to be now 1, and then the next one's going to be 2b minus a, like that. All right, and here, let's just bold this one out. Or just box that in. And the next line, line 2, this was the same thing, x equals a plus t, but then it was y equals b minus t, and then we had z equals to c minus 2b plus a t. All right, so separating this, we get, well, r2 in vector form equals to a, b, c, so point on the line, plus t, and this is going to be 1, erase this bracket, 1, negative 1, and then we're going to have negative 2, and then b plus a, like that. All right, let's just box this in as well. All right, and finally, we can graph this in GeoGebra, and so here's our equation: z equals y squared minus x squared. And then what I did was, just use the variables L, M, and N, just because I already used A, B, and C in my earlier exercise, and I'm using the same link here. So we'll just use L, M, and N. So this one is X. Oh, I mean, this is A, this is B, and then this one is C. Yeah, so that's A, B, C, and you can see that here. So we have L 0, M is 0. Just we could slide it across and see the different lines that are formed. And then the N or C is equal to M squared, which is Y, minus L squared, which is the A squared. So in this case, we have 0, 0, and 0. In the line, to put it in GeoGebra, you could use 2 lines right here. I mean, 2 points on the line. So line 1 is L, M, and N. And then another line is just when this lambda, or this is actually t, just set it equal to 1, and then plug that in. So we'll have L plus t is just L plus 1, M plus 1, N plus 2M minus L, like that. And then same thing for here, L2 is L, M, and N, then L plus 1, M minus 1, N minus 2, M plus L. These are just points on a line. And they automatically graph this point, they automatically calculate the vector equation like this. So we'll have 0, 0, 0, and then lambda 1, negative 1, and 0. The first line is 1, 1, and 0, and there's that lambda or t. It becomes like that, yeah. So if you plug in 0 right here, if a is 0, you're going to have, yes, this is going to be 0, 0, and 0, and then this one will be just 1 when you have t is 1. And then this one's going to be 0 plus 1. This one's going to be 0 plus, and then it's going to be vanishes all to 0. Hence, you'll have the 0 there. All right. Now, here's how the line looks like. So those are just the basic line from the point at the origin 0, 0, 0. And look, and notice how it cuts perfectly in line with this saddle or this hyperbolic paraboloid. And let's go and graph this out. So here's this is actually the sphere or the Earth from my earlier exercise. If I plug this in, it gets really big. And then here and here. So we got to zoom in a whole lot because and then I'll hide this. And now we got to zoom in because the scale was for the Earth was 6,000 kilometers. The radius 6,000 plus. So we got to zoom all the way in until we can see this setup here. So we're going in and in. Keeps going. Yeah, just to illustrate the scale. All right, we are almost there. All right, there it is. That's pretty cool there. And notice the line is perfectly in line with it. And we can shift this down. Whoops. Yeah, just shift this here. And then rotate it. Click this and rotate. So it looks something like that. And now what we could do is we could adjust, we could slide this value. If we slide M, then all the values, or the N is going to change. So you're going to have a line that's like this, and it's going to be, it's still going to be on it though. And yeah, so you could move it around and see the line there, and we could change this L or the A, and notice the lines change. Yeah, so that's pretty cool stuff there. And then, yeah, so the lines change, and you can still see it's always going to be on the hyperboloid. So you change it up, and you could press play, see what happens here. Press play as this one as well. See what happens. So it's always going to be on the line, yeah. So it's literally on the line always, which is quite amazing. So you can make this all with lines. That is called a ruled surface, which is quite amazing. All right, stop and stop. Epic stuff. All right, so I'll continue further. Yeah, so that is all, and that's yeah, that's pretty epic stuff there, and hopefully you enjoyed. And yeah, that's all for today. Hopefully you'll enjoy this, again, another giant long video, and I'll be working to put this all into smaller sections in a playlist, or sections playlist, and so on. And yeah, hopefully you enjoyed this, and it's pretty epic stuff here. The graphing, especially the manual graphing, like I did, is very tedious, but you understand a lot of the ins and outs of it. And also, again, remember the graphing calculators and the computers, they have to do pretty much what we're doing here manually, and uses traces and so on to graph it and simplify it and so on. So that's what they do, but automated. So it's still, again, important to understand this. Yeah, especially if you're working in computer graphics and so on, or just understanding mathematics and what's going on behind the computer. And they might help solve problems you didn't know existed. Anyways, that is all for today. Thanks for watching, and like always, all the links will be in the description below. Yeah, and that's all for today. Thanks for watching. Stay tuned for another math easy solution.